Yeah, welcome to the mathematics and the new video. Today we want to talk about matrix factorials, and our plan is what we want to find. Our goal is if we are given a matrix A, let's say a 2 by 2 matrix with real entries, we want to find matrix A factorial. And to do so, we go step by step, and first our plan is, so first we discuss what is the matrix factorial if the matrix is diagonal with the same entries on the diagonal and with natural entries. Then we extend the diagonal matrix to the reals. The third step is if the two diagonal elements are different, how we can take care of that. The fourth step is an arbitrary 2 by 2 matrix with real entries, and A is diagonalizable. Diagonalizable. How to write that? Diagonalizable, like that. Then we should take care of an example, and the last is a nice result from this matrix 0, 1, 0, 0 factorial. And before we can come to our plan, I also want to recall from linear algebra, if we have a matrix A which is diagonalizable, then we can find a permutation matrix P. And we can find a matrix P which is built from the eigenvectors, and so we can find the matrix A bar, which is diagonal, and the entries on the diagonal are the eigenvalues. Alright, so we will not discuss this in detail, I just want to recall it. We will make use of this property, and also I want to remember of the gamma function. The definition is integral from 0 up to infinity, t to the power x minus 1 e to the minus t dt. And with this definition we have a nice recursion. Gamma of x plus 1 is x times gamma of x for all positive reals. And if this x is natural, we find gamma of 1 is 1 and gamma of n is n minus 1 factorial. And with this nice recursion here, it makes sense to say that gamma of x is a nice extension to the for the factorial. Okay. And we will make use of this reduction formula or the recursion. Okay, I just want to recall that. So let's tackle our first point of our plan. And by the matrix, by the definition of the matrix multiplication, it makes sense to define this matrix factorial this way, and therefore we find n factorial 0, 0, n factorial. Okay, so this is a really easy idea, and yeah, a first this gives us a first idea that we can make sense of a matrix factorial. Okay, so I let you guys think of that. So this is our first idea. For a matrix with same elements on the diagonal and natural entries, it makes sense to define the matrix factorial via this way. Okay, so it's a definition, and yeah, it makes sense. So our first step of the plan is done. Okay, and yeah, and the second step, if we have real entries on the diagonal and we want this matrix factorial, if we take a look at this one, yeah, it makes sense to define it in this way. Alright, so there is no reason not to do it. We have the first part, and now we extend the diagonal on the reals, and this makes also sense. Alright, and now you can see if the diagonals are different, and also by the definition of the matrix multiplication, you can see that this is also a very fine definition. Nothing goes wrong. There is no reason why not to do it in this way. So the first 3 points are done. Alright, so please pause the video and think of this. Now the interesting part is 4. Alright, so I clean up the board and then we can take care of the fourth point. Yeah, on the last board we discussed that this is a fine definition and also these two is a fine definition, but I forgot I've forgotten one thing to point out, and this is that our target, I just want to make it clear. I forgot to point out that if we have gamma, this is our goal from a diagonal matrix with real entries. What we like to find is gamma of this matrix, let's call it A. We want to find A plus the identity matrix to check the recurrence relation. And it would be nice if this is exactly what we want, so this is what we want. And yeah, to do so, so we check this this equation. So if we have the matrix A and we multiply it with gamma of A, which is this matrix, now we can easily check that we get x, gamma x, 0, 0, x, gamma of x. Now gamma of x is gamma of x plus 1. And this is by our recurrence relation, and this is exactly what we want. This is gamma of A plus the identity matrix. Okay. Yeah, so we showed already that so here everything goes well, and this is what we want to find, and now this is done. Okay. And also you can check easily by the definition of the matrix multiplication, yeah, that nothing goes wrong if we plug in here a y, then also everything goes well here. Alright? Yeah, and now we can take care of the fourth point, and therefore I clean up the board again, and then we can tackle our goal. Okay, on the last boards we discussed that the matrix factorial for diagonalized matrices is meaningful, and also this recurrence relation with the gamma function works fine. Now we take care of an arbitrary 2x2 matrix, and we let A be also diagonalizable, and now we try to compute this recurrence relation, and therefore here we start with gamma of A plus I, yeah, and I is the identity matrix, and this is already diagonalized. A is diagonalizable, yeah, so we can find in the first step this, so first step is P inverse times gamma of A plus I diagonal times P. Then the diagonal and so we can split this up. A plus I is diagonal, so I is diagonal and A is diagonal, and I is of course diagonal, and now we can apply for diagonal matrices. We've already checked this. We know already that this is that this part, so the recurrence relation holds for such matrices, and therefore we can multiply by the identity matrix in following way. Alright, so here we put up P times Pm inverse, and therefore the first part is A, and the second part is gamma of A, and therefore we have what we want. We have our recurrence relation also for arbitrary matrices. Yeah, and therefore we can make sense of the matrix factorial. So A factorial is gamma of A plus 1, A plus identity matrix. So this is our final result. We can define it in this way, and we know how to compute this stuff. And this is, yeah, what we would expect more or less. And we have checked that this here everything goes well. So 0.5 4 in our plan is also done. And yeah, now we can take a look at an example. Therefore I clean up the board and then I come back. Yeah, our last step is we discuss an example, and what is a very nice example? We give the full solution of a 2 by 2 matrix, and therefore we let A B, C, D, and we calculate the eigenvalues. You know, it's a zero. They are the zeros of the characteristic polynomial. But we will not go through all the details. What we get at the final result is the trace of A plus minus the square root of the trace of A squared minus the determinant of A all over 2 minus 4. So trace squared minus 4 times determinant of A. Okay, these are the two eigenvalues for an arbitrary matrix, and yeah, under the assumption they are real and they exist and so on. Okay, and therefore the eigenvectors, we can compute the eigenvectors. V1, it's the vector minus A plus D plus this square root from above all over 2 and entry 1 2C, and V2 is similar, minus A plus D minus the square root all over 2C and also 1. Yes. Alright. Yeah, these are the two eigenvectors. Yeah, and let's see. Yeah. So at the end what we find, so if we diagonalize our matrix and we make the gamma of it, so the matrix factorial, the full solution is given by V1 V2 times bigger matrix gamma of A plus D minus the square root, so the discriminant all over 2, 0, 0, gamma of A plus D, so the trace plus the square root all over 2. And then, yeah, the inverse of this, I will not write it fully out, something like that. This is the full solution of the matrix factorial of an arbitrary 2 by 2 real matrix. Yeah, and for the last point, yeah, you can try to compute this matrix. What you get is, we find 1, 0, 1 and the negative of the Euler-Maccaroni constant gamma, And how to compute this, we only discussed diagonalizable matrices in this. For this part, yeah, we use the Jordan decomposition, and yeah, you can check this by yourself. Very nice result. Also the Euler-Macroni constant shows up here, and I hope I did not a mistake during the calculations, and yeah, but I guess you get the idea. So I hope you like this video and the topic. See you next time, and bye bye.